partners. Charles is both an architect and an engineer, which is obviously a very good start in thinking about how to research and to apply these sorts of technologies. He's worked in different firms of architects, including with Ron Arad and Michael Hopkins, studied at Imperial College, and has worked, I think, recently with architects including Ben van Berkel, Alvaro Caesar, Daniel Liebeskind and Rem Koolhaas. And again, wonderful experience of seeing technology open up before you like this. But I think I'll leave Charles to explain exactly what you're going to say.
Okay, it just takes a minute to start out. So. I think that's because the yeah. I'm used to sort of starting it up before plugging it in, actually. Okay. There's one thing I can try doing it blind, actually. Ah, okay. Need something now. Okay. Just wait till it starts. Sorry about the size of the PowerPoint. Okay. Okay. Well, within the context of emergence, I've got this talk sort of structured in two halves. So I'll talk for about 10 minutes, and all this sort of theory really lies here. And then I'll just take you through a series of about 6 or 7 projects that the group's done over the last few years and kind of illustrate what I mean. But I'll go fairly quickly through them because there's a fair number of slides. So within the context of emergence, I just want to talk briefly about the relationship between architecture and engineering, or in a way, the relationship between form and technique, with technology, in a way, being the incubator of technique. Engineering is about making things, technology, while architecture is about making spaces, and this relationship between the material stuff and of the building itself and the space in its kind of broadest cultural sense that the building contains. Oops. So why is engineering relevant today? Well, architecture has been trying to develop a new language of technical forms born in our digital age. But has the attempt to revitalize architecture from the direction of digital formal manipulation failed? Is the invention of emergent forms the task of architecture, or is architecture more and different? Architecture, where it became great, was almost always indebted to construction, and construction was almost always the conveyor of its spatial form. The Romantic and Gothic display that in brilliant clarity. The structure expresses the meaning, expresses it down to the last remnant of spiritual value. And if this is so, then it must follow that the revitalization of architecture can only come from construction and not by means of arbitrarily or aesthetically assembled forms and motifs. Oops. But construction, that loyal safekeeper of an epoch's spirit, rejects all that is arbitrary and creates an objective basis for new developments. This is the objective technical world of the engineer. Mies described the few authentic structures of his period exhibiting construction as a component of building. Building and meaning are one. The manner of building is decisive and of testimonial significance. Construction not only determines form, but is form itself. This may also be the reason why the 19th century failed. Unsuspected and deep beneath all the confused attempts of the time, and by that I mean the kind of Beaux-Arts and the pattern books of the late 19th century, ran the quiet current of change, fed by forces of a world that was intrinsically different, and a jungle of new forms broke out, unusual and of wild power, the world of technical forms, large and forceful, genuine forms in a genuine world. Everything else that occurred looked next to that, pale and marginal. But technology promises both power and grandeur. To the careful, however, beyond all prejudices and misjudgments, technology appears as a world which is what it is, specific and narrow, dependent on the panorama of its own time, just as any other epoch, and precluding a host of possibilities. Today we live in an era that I would describe as one of transition. The mechanical paradigm that Gideon isolated so successfully in his tome, Mechanization Takes Command, is being supplanted by new forms emergent in a new digital age. Today, like the 19th century, fed by the forces of a world that is intrinsically different, a jungle of new forms is breaking out. These forms are born in a world no longer governed by the mechanical paradigm, but in a fluid world of integrated digital technology. Unlike the mechanical, these forms cannot be discretized into finite components, but operate in a highly integrated way, multitasking with hybrid and integrated performance. As Mies described, some talk of fashion, others talk of timelessness. Neither is right. Architecture is beholden neither to the day nor to eternity, but to the epoch. And only a historical movement offers architecture space for living and allows it to fulfill itself. Architecture is the expression of what historically transpires, expression of an underlying cultural movement, fulfillment and expression of something imminent. If this is true, then the new digital technology today must change into architecture to complete itself. But none of this comes about by itself. History does not come about by itself. It must be done. And historical measurements are shorter than many realize. Only 30 lifespans separate us from the Acropolis, and the breathing space of the Middle Ages was too short for it to complete its cathedrals. So where do we stand today? About 70 years ago, a new approach in technology began to emerge, more holistic and less mechanical. Unlike mechanization that involves the discretization of a system into its component parts, this paradigm proposes the integration of the various components of a system into an isotropic integrated whole. With the birth of the integrated circuit and the information age, integration took command. Within architecture and the contemporary context, this approach increasingly synthesizes disciplines and new working procedures and networks. New architecture inhabits a section through many spheres of knowledge. Structure, which has always ordered architectural space, can no longer be seen as discrete. Digital technology has created a new order with regards to form, function, methods of production, and materials. New strategies are needed. Holistic strategies that integrate structure, programmatics, circulation, surface, sun shading, aerodynamics, building physics. New opportunities will be evaluated for their potentials across disciplines. It's a certainty with this kind of complexity comes opportunity. Therefore, it follows that he who controls the tools controls the outcome. And it's the control of these digital tools that we seek. That's the theory. These are the projects. So I'll just show 5 or 6. Starting with a project that actually I was involved in before I joined Arup. It started 10 years ago in 1994. It's the Singapore Arts Center. And our brief was to develop a dome over 2 opera houses, an opera house and a concert hall in Singapore. And the intent was to make these domes kind of like the kind of leaves that sunshade public spaces in that part of the world. And we developed a kind of concept model that looked rather like this, with no real understanding of what the building would be, how it would operate, or really how this would be mapped over the surface, nothing. In a way, developing just like the DNA of the building, if you like. But intended as an integrated DNA, the building envelope integrated with structure, integrated with sun shading. And we were invited by the client to proceed. And I'll just talk about some of the people that were involved in these projects. So there was a young, at Atelier 1 at the time, there was a young engineer, or a young architect, Barnaby Gunning, who discovered this NURB surface facility in MicroStation. And after a lot of research on soap film surfaces and so forth, we decided to use a NURB surface, which is a kind of arbitrary surface description that comes from computer gaming and animation, mainly. It's based in projective geometry, and basically uses an equation to describe with engineering precision a very amorphic surface. So Barnaby discovered that, and we mapped a sort of tight fit, soap bubble, if you like, over these 2 domes. And then there was another engineer who was involved in a lot of the structural analysis, Chris Hornsey-Jones, an aerospace engineer, who came with the idea of the equal link-length mesh, which is a bit like Mannheim. It's a mesh of, the Mannheim grid shell from Auvert and Friado. But in our case, it wasn't intended that we push it up. We were just using this as a tool to map the surface. So it's like if you imagine a kitchen sieve. It has fibers in 2 directions, but then to impart double curvature, it would lie flat like a screen. But to impart double curvature, you sort of shear it together as you press it over a dome shape. So the quadrants in the 4 corners lozenge, and the included angle between the members closes up to kind of allow you to tuck the surface together and curve it. So we mapped an equal length mesh over the dome by swinging arcs, but because the surface falls away, we had to swing spheres. And I mean, now at Arup, people like Tristan Simmons just write a patch, and we've got a mesher that puts a equal link length mesh on any NURB surface kind of from a position with a given orientation. But at that time, we were working pretty crudely. So it's sort of, if you like, hand modeled in the computer. And after we developed these meshes, we sort of mapped and described the surface. This was an effort to establish, because all the glass panels, triangular glass panels, would have different angles, always 1500 on two sides and a different included angle. So we're trying to map bands of the variation in the included angle so that you could have a standard double glazed unit. And then one of the curious things that sort of arises out of, through really serendipity in a design process was the fact that along one of these kind of geodesic projections through the mesh, you can see the included angle here is greater than 90 degrees, and it reduces down to 90 degrees around this point and further down here. By taking one standard diamond shape and fitting it in that bay, as you develop across the surface, that angle folds and the sun shade bumps out, which Singapore's on the equator and this building faces north and south, so it excludes light from the east and west and allows views north over Singapore Harbor, and at the back it allows views south out of a rehearsal area. So there's the finished construction. There's a couple interesting things along the way. Mero won the tender for the structure, and I don't know if you guys know the Mero. It's a spherical connector in a space frame system developed by Max Mengringhausen. And for years they just drilled 4 holes at orthogonal angles for the bottom chords and 4 holes for the diagonals, and it's a single bolt that goes into the holes. But they'd been tendering for that project with Frank Gehry and Pariser Platz for the ING bank, that curved grid shell. I think Schleich ended up engineering it. But they wrote an interface between their proprietary geometric modeler and the lathe that drills the balls. So in Singapore we have 20,000 nodes. They're all of one type, but each one is CNC cut specific to its position. So each of the nodes, you can see the space frame in the background here. So each of the nodes is stamped with the north arrow on the top for the installer so he can orient it, because it's a bit of a puzzle, yeah? And they're all bar-coded. And when he opens a box, they would swipe it. It all had to be packed in the right sequence for unpacking on site to assemble in the right order. And they used a kind of parcel tracking system to track like the logistics of where every component was on site at any given time. And similarly, you get the similar kind of complexities with the glass, same thing, each glass piece numbered and so forth. Mero chose, because most glazing systems leak at the gasket, they chose to go with a standard and parallel joint at the gasket and cut every piece of glass specific to its location. And curiously, I didn't think that was economical, but found out later that all glass is cut off jumbo sheets by a computer, even if it's rectangular, and there's an optimization procedure that takes place so that the glass comes off the bed and is broken in a certain sequence to break down into smaller rectangular pieces. The cost is, if you go to triangular units, most of the cost of glass is in the edging, grinding the edges. So normally it goes into a jig and it's ground and flipped and ground and rotated and ground because it has parallel edges. If you go to triangular, your glass is going to be about 30% more expensive because it has to be edged manually. But once you've gone to triangular, if every triangle is different, it doesn't matter because it's being edged manually anyway. And it's cut off a computer optimized process anyway. So the on cost of triangles was 30% on the glass package. But then the on cost of every triangle being different was only 10% above that for the kind of logistics of handling it. So that in a way, I think there's a new type of standardization, which I would describe as topologically standard components, but you could have an infinite number of conditions within that. So, of course, we couldn't keep attic stock of double glazed units because if one breaks, what we did, they're keeping attic stock of jumbo sheets, and they have a manual. If they break a double glazed unit, they have to rebuild the double glazed unit and replace it. Here's the finished project on site. Well, after that, I kind of realized that those buildings faced exactly north, south, and east, west. And as I said, Singapore's right on the equator, so the sun moves directly from the east overhead. But I thought if the building had been rotated through 30 degrees, the whole sun shading system would have had to be developed through an asymmetry, and perhaps the surface of the dome. In a way, in Singapore, we held on to symmetry, because although we knew that there was an incredibly complicated geometry, somehow the symmetry gave you a kind of basic reference. But after that, I realized the symmetry was irrelevant. And I wanted to kind of work on a project to take space frame and almost like start bending it and tearing it and kind of like weaving it like a pretzel. And so this project came up, which Cecil Baumann and myself did with Philip Johnson. It's Shivas Park. It's a kind of crazy proposal for Liverpool, which went to a major public inquiry and was eventually declined planning. Which was probably the right decision, actually. But we were only really involved in the roof. So underneath, it's a shopping mall, and it's completely banal. And there were concerns that the developer wouldn't build the roof once he got underway. So the surface is, well, there's an image of it. It's, the idea was that it would be, rather than spanning laterally, we'd span longitudinally. It's quite long, 300 meters long, 100 meters wide. And the idea was along its length to develop kind of crescent arches, a bit like this, to take the punch holes in the surface and kind of drag it down to the ground. And then through these kind of folds, develop the surface into a folded plate that would span longitudinally, and then be supported by a series of crescent arches, but which importantly are not all in alignment, where you'd be setting up this classic arch buckling mode, but they're all staggered against each other. So through the body of the surface, there's a kind of inherent bracing against arch buckling. And this is a model produced by Francis Archer, one of the guys in the group, very clever engineer with a mathematician's background. And here, all the arches are modeled as space frame, and the areas of anticlastic curvature, which is the saddle shape, in which you can have you could have fabric, because like the curvature of the warp yarns pulls against the curvature of the weft yarns. So here we're proposing cable net as an infill between the arches. But of course, following the general rule of lightweight structures, the less you see, the more it costs. So curiously, a full space frame solution was much, much cheaper. This is just a daylighting study, daylighting factors. The idea was under this canopy to create like the Riviera in Liverpool. And then this is a view of the solid model just before we built a rapid prototype, that STL, the resin model you saw earlier. And here's some of the structural analysis, where you can see broadly these purple lines indicate the compression moving through the arches. And here's analysis of a full space frame option. This is a project that we're involved in with Shigeruban. It's in St. Louis in the States. And it's a timber grid shell. It's a bit like, it's in a park called Forest Park. And it's a bit like, sort of like a serpentine pavilion type of scenario, but this is a permanent picnicking pavilion. And it's a reticulated timber grid shell using discontinuous boards. So what's quite nice is we're using the boards. The boards are straight, and they're offset against one another, so they overlap each other at the connection. So through this kind of small overlap at every connection, you develop a small amount of synclastic curvature. And similarly, if you overlap the boards in the opposite direction, so clockwise, that was rather than clockwise spiraling upwards, if you go clockwise spiraling downwards, you'll develop synclastic curvature that's concave upwards. And you can also develop anticlastic curvature. So one of the guys in the group, Tristan, wrote, well, actually, he just used within our analysis software, like our nonlinear solver, there's a tool where, as a kind of pre-stress load case, you can apply a lack of fit to a structure. So what we do is we just build the whole grid flat, and then the overlap is applied as a lack of fit. And what happens is when you run the analysis, the surface just bumps up into the curvature that it takes. And so so here's a model where they're spiraling, concave, or they're spiraling downwards in this direction if you go counterclockwise, and upwards counterclockwise in this direction. So the surface that develops has both curvatures. And one of the guys in the group, Benedict Schleicher, who I think I saw here earlier today, went with Shigeru Ban to Rice University, and they built this 1/2 scale mock-up, which demonstrates the kind of the system. What I find particularly interesting about this is it's not it's not really a form-found surface, but the surface has very specific properties, because you can see the boards here are curved, and the geometry doesn't just move into a state where every board is straight. There's a lot of locked-in internal stresses. There's a lot of embodied strain energy inside the surface once you've kind of applied all these twists. Now or all these overlaps. We have to make sure that it's not too difficult for the people on site to assemble. Otherwise, they physically won't be able to manhandle the boards into that position. So we have to study those locked-in stresses. But also, the surface itself is developed through not just straight geometry, but through the kind of the inherent qualities of strain energy within the surface. So it's kind of like an integrated geometric and statical surface operating at the same time. So that's just beginning on site a little later this year in St. Louis. And these are just studies for the column. The idea of putting little plates inside the smaller squares in a kind of bundled column. This is the Ito Pavilion, which I'm sure many of you have seen. This is Ito's original proposal. Either he had a couple of strategies, but these two both refer to the idea of a beautiful box. The one on the left is a little bit like a pavilion he made in Bruges, and the one on the right, he drew on some ideas. He'd seen Cecil's proposal for Chemnitz Stadium, and he was interested in the idea of the use of algorithm to develop geometry. And you can see his original models, which are effectively like just a chaotic arrangement of bars, which certainly would have been possible. I mean, we could have just solved that and built it. But somehow, Cecil felt strongly that there was a kind of underlying inherent order that could achieve the same kind of, or even stronger visual quality. And he and one of the engineers in the group, Daniel Bozia, found this algorithm, which is incredibly simple. It's just taking a square, going from a half to a third, half to a third, half to a third, developing the square as a ziggurat, and similarly going from a half to a third, developing the square, and so on, and then until you get this pattern, and then extending the lines out to infinity. So, in that pattern developed the entire geometry of the pavilion. The center of the square is offset, otherwise all four elevations would have been the same. And that's exactly how it was built. This shows it's still before this center of the square had been moved off. But it was built through a panelized system, so it's literally a ziggurat of steel beams with all the members off the side here are just purlins that restrain that steel flat against lateral buckling. And the panels were built in sequence, kind of spiraling toward the center. And we used with William Hare, steelwork fabricators, we used this package X steel because I think there's about 1,500 plates here. And quite importantly, all the plates had to be cut square, and because they were cut off of out of large plate with a laser cutter, and or off of strip, off of bar with a laser cutter. So, but the exact line of that cut related to the thickness of the plate that it came against, as well as the angle that it came against that plate. So X steel is a kind of package where you basically build a virtual building model of all the steelwork. So there's no shop drawings involved, and each plate is stamped and cut. And so you can see, it was only later that Ito decided it was really because of this solar heat gain. Originally, this was a glass pavilion, as per the earlier models. And there was a sort of standoff between us and Tokyo when we told them, it's going to get too hot inside there. And some of it has to be opaque. And it was sort of like, 15%, 20%. And finally we said, no, 50%. And then there was about a kind of 10-day radio silence. And then this fax came through with this checkerboard. And, well, we had to do it. Like, the problem thing is, like, it just sort of made a mockery of using steel flats because we could have braced everything against buckling inside the opaque panels. But that's life, yeah. So you can see here the way these flats have to be cut short. It was incredibly complex system, and every plate cut, stamped, and then it was welded in one piece and then broken up afterwards before being painted and brought to site. And there it is standing in the park. This is a project we did with Chris O'Feely and David Adje for the Venice Biennale. It's a little glass ceiling in that was indoors inside the British Pavilion. And Chris had this pattern of a 7-pointed star that was a motif that ran through all the paintings that he was showing. And he asked us to make a glass ceiling, rather like this pattern. So these are some of the early models. We use we have a thermojet in the office, basically used for visualization. And what we eventually developed was a circular arrangement with 7 septants of standard geometry. And Daniel Bosey in the office wrote a little routine where from the center of gravity of every panel, they were distorted out to match this slightly coffin-shaped perimeter of the room. And then once we'd mapped the geometry, we took center gravities, and Lip Chong, a student of Michael's from Tip Unit 4 who's working in the group, did all the collision detection in the computer so that we knew none of the panels were hitting. And we identified the center gravity of every panel. And from that point, put in a space frame node with half of the nodes at high level, half at low, and developed this kind of slightly eccentric space frame topology. So these are the bars that the glass is glued to, and that's top chord of the space frame. Those are the braces, and then the bottom chord of the space frame. So here you see this kind of eccentric space frame geometry relating to the center gravities, and then with the glass beneath. And we got Marot to make the space frame for us. Structural analysis is nothing particularly of interest. And that's the model of the ceiling inside the hall in the British Pavilion. And you can see it was a very beautiful space frame, actually. These are some of the drawings. And the glass panels with the structural silicone. And this is the assembly on site. We were very limited because of time on the color of the glass, which I think was a great disappointment to the success of the installation. But here you can see the kind of motif in the glass ceiling. You probably know that you've probably all seen the Marsyas. The project, I suppose, what's interesting and what we've learned from Anish Kapoor is that Tristan Simmons, who was the engineer, slightly modified our software. Because it's indoor, it's extremely light loading. Normally you're looking for, in membrane structures, to find a uniform stress distribution. But you can actually nip and tuck a membrane rather like a suit. So after you've found a surface of minimum area, you can begin to tweak it. And Tristan worked incredibly closely with Anish to kind of tailor this into the exact sculpted form that he was looking for. We spent about 3 mornings from 8 till 10, or maybe even longer, sometimes 11, 3 days a week for a period of about 5 months before he was happy with this. It was quite amazing to look at somebody who works with, such control over their medium. And just there's the installation coming in on site and being stressed. And the finished installation. The steel ring was impressive hanging, but effectively, you can see in these joints, there's actually a nylon webbing belt that runs the full length of the hull, and that's a 150-meter long catenary. And then the membrane in this area is effectively hanging across those series of belts. the thing was, when you're inside the space, you couldn't actually see the catenary. You couldn't actually, so you had no idea how the ring was supported. Okay, this is the last project I'll show. It's the one we're working on now. About 6 months ago, we got involved in master planning at the Battersea Power Station. And the group is involved in this whole area, the South Park, but I'll just show this one office building that we call the Twist. The form arises out of specifics of the site, but the important quality of it is the client wanted it to be permeable to the community beyond at ground level. So it lifts up off the ground and then comes back down on the opposite side. And there's a core at either end. And the main problem is spanning 60 meters between these two cores. So beyond just the twist in the external form, here you see the cores. We've looked at a system of running trusses across that space. So the idea was to take, within an atrium space, to take the edge of the slab and actually twist it up and develop some kind of truss profile through the atrium. So here you can see the surfaces twisting through 180 degrees. And also through that, this building's used as a kind of showcase building for products. So they just want people to be able to move through it in many different ways. And so what we're trying to do is integrate like a circulation paths with structural trusses. So this is a kind of quick build-up of that atrium zone and the floor slabs that relate to it. You can see there. And then from the center, it's built up in this way. And a laser cut model showing the routes that one can take through the building. So here you can sort of see this isn't the exact solution, but the kind of bending moment profile between the two cores and in plan. So the plans are kind of curious. You get this atrium zone with twisted trusses. And similarly in section, you get a very regular section at the one end and then going through this transformation as the twist passes through space. And this is a kind of fairly crude model showing the buildup of the trusses and then the steel composite flooring going in and the atrium space in between. So that's getting pretty close to the structural solution for that atrium zone. And there's a short animation here, just kind of moving around the building. And so the intent is you enter from the southwest corner. This is going to be a building, hopefully by you in studio if we're successful in securing their appointment. And then there's a route on the right through a kind of public space at the lower level and then into the center of the square. You can see the cladding hopefully will be a kind of opalescent, not necessarily diachroic glass, but something where you can see the reflection of the city, the overall form, and the activity of the building beyond. And there's just one more slide of this, which is quite a subtle one, but it shows the system of triangulation that we're intending on the facade. And just to give you an idea, like basically the twist is defined by two splines, and then it's just the surface is just lofted. So there are straight line generators, and in the system of triangular facets, those straight line generators form one set of joints. The second set is formed by the floors themselves, because you need, in a cladding system, you need kind of fire compartmentation and isolation between the floors. So there's a second line that passes through here in the jointing. And then the third line is just the diagonals which that forms. But what I find really remarkable is that the kind of resolution of this diagonal edge of the twist has actually been integrated within the triangular system of the glazing. And I think it's that kind of subtlety in the formal manipulation and the kind of constructional logic that forms the basis of the kind of building that, and that kind of integration of performance that we seek, both in projects like in Singapore or here in London. Just to end, always show this, Sydney Opera House. You know the story, Johann won the competition, and with a very loose sketch, which I'll show you here. This is actually one of the competition drawings. These very amorphic shells. There was only suggestion of a ridge at the top, probably because I don't know why, maybe he couldn't draw the ellipse. The way it was rationalized, famously, is segments of a sphere. They're all surfaces off the same sphere of one diameter, and it's with this kind of orange peel, this kind of orange segment type mapping of precast elements. So every one of those precast elements could be struck from the same mold, although at a slightly different length, and then with an in situ concrete stitch at the top. And that mapping of the surface runs right through to the cladding tiles and the actual ceramic tiles on the concrete tiles that clad the entire building. And I just wonder today, like, it strikes me, it's very much of its time. It uses techniques of precasting, mapping a surface as a platonic, spherical surface. With the tools that we have today, with NURB surfaces, with CNC machining, if you kind of reenacted the competition and a contemporary engineering team took it on, you'd end up, well, equally with the building of its time, as is the Opera House, but of a totally different constructional nature.
Thank you very much, Charles. Talking about applications in very different circumstances and conditions with very different outcomes. It also, I think, Charles's talk helps very much to make the link between earlier contributions, talking about from the theory through to the design conceptions and then into realized projects. And now, for our final talk this afternoon, we have Johann Sischka of Wagner Bureau, based in Vienna, who's going to talk about manufacturing complexity, something that he's done, I think, quite a lot of, particularly in projects such as the roof over the Great Court of the British Museum.
Okay. Good. No, thanks for the invitation. And just saw that my computer is switched off, so I think it takes once again some time to get it onto speed. Maybe it comes easy. We'll see. Working now, isn't it? It's once again off. It's okay, yeah. Sorry for the problems, but I think we've resolved them. What I would like to do is, we've seen a lot of forms today, and I think some of them would be quite challenging to be realized, and I'm happy that we had some easier forms to realize in the past. I think it is not on. Here we are. Okay. I would like to explain a little bit how we were able to realize the ideas created by the architects, created by engineers, to really produce them, to make them, to install them. What are the aspects there? What are the means we can use? I think one important topic, of course, is costs, economies. One can create the best and most complex structures if they are too expensive to be realized, if they take too long. Return of investment is a very important word. Once the idea is born, it should be realized within some minutes, or at least some days or years. And I think it is very important to use the computers also to realize the structures, and that's something I would like to explain to you a little bit. I want to start off with one of the earliest projects where we were involved, and which gave us the opportunity to learn a little bit more about how to deal with geometry, which is the dome of the Reichstag in Berlin. It's a Foster project, and the engineers were Leonhard and Dreh and partners. Just the principle of it, the dome sits on top of the building right in the middle, right above the chamber, and one of the topics was to get daylight into the building, into the chamber. And here you can see there's a skylight on top, which is the watertight level of the roof. You got the light cone with a lot of mirrors onto it, which reflects the daylight into the dome. And another feature, which is quite popular, you got the ramp, 2 ramps going up there to a platform where the visitors can go up even if they have meetings in the chamber. And finally, you got the sunshade element, because the mirrors are highly reflective, and if you get the sunshine into the chamber, it would be inconvenient. So there's a huge sunshade element in front of the mirrors, which are orientated to the sun and which travels around with the sun. That's the simple form of the ramp. Because it follows up the curve of the dome, it always changes the radius constantly, and it also moves away from the dome to get enough headroom. To make our life not too easy, the architect has created a form which is not rectangular. It's such a box section. Mainly you need the box section for the stiffness, and it got glass balustrades on both sides, and here there's space for installation, electrical installation and mechanical installation. The ramp itself is only hung from with 1 bolt on the outside to each second rib of the dome. What we did when we developed the computer program to realize it, we started off with the curve, which is the one which was given by the engineer. We also had to calculate the level of pre-camber once the load is released to get it horizontal. And what we did, here you see the section, we just put the section every 25 centimeters along the curve with the right pre-cambering, and then we combined all these profiles to get the shape, and then we created the plate out of it, which finally was unfolded to be cut. And here you see the various elements, and this is the principle of how we fabricated it afterwards. The only thing which was constant over the length of the ramp was the section. So we created these forms which represent the section, and we have reassembled them onto a flat plate for each individual ramp section, and then we laid out the profiles inside there, as you can see here. Here you see the plate which goes into this form, into the template, and here you see how we marked the positions of the other plates which have to come in, and so we finally reassembled the whole structure. In order to have some damping system on the top plate, we used another plate and some glue in between to damp the ramp, because it's a hollow body, and if it's above the chamber and people walk down, it shouldn't create any vibration. The rib itself was fairly easy. It's once again a triangular shape, but it follows a curve, and all of the 24 ribs are the same. There was no diagonal bracing involved, so here you see in an oversized manner the deflection you get during the wind, from wind speed, and the moments you need when you introduce the horizontals here. So we needed a fairly stiff connection, which was done by this cast element. Here you see it in reality. Coming back to the sunshade element, With all of the jobs, I do learn a lot, and on this one of the things I learned is a little bit about what the sun does over the year. And as I'm sure you know, it doesn't go constantly, so we had to find a control system which allows the sunshade to move in the right speed, with the right speed, to be at the right position at the right time, which is different on every day of the year. Here you see the platform on top where the ramp comes in. It's 12 hangars where it is supported from the dome, and this is a ring which is running underneath the platform and where the whole element, the whole sunshade element is hung from. There is no other support at the bottom, which was originally planned, but we could get rid of it, so it's just a cantilever coming down. That shows the technical detail and some of the issues we have to deal with in the discussions with the architects. This is the ring beam of the platform. Here you see the ring of the sunshade element supported by these rollers. This one is driven by a friction drive with a frequency converter on the inside. Here you see spots. That's the fixation for the balustrades. And you can imagine there's no real space left for anything else. So it took us more than a day to get to this solution in the discussions with everybody. This is the main frame of the sunshade element, pre-assembled in the workshop. What you can see here, that welding always means distortion. It's bringing in heat. It changes the shape slightly, so we had to heat treat it afterwards to find the shape. That's another view. That's where the top ring comes in. And that's a nice picture, which I like quite well. When we delivered these elements to site, you can see how the shape really is, and it looks wrong, I would say. It doesn't look right. They don't follow up the curve. They don't seem to fit together, which was subject to some comments at the time. But the next picture tells you that what obviously isn't right is right, and when you put it together in the right manner, in the right sequence, it comes up with what we want to have. And this is the final product of the sunshade element. That's the dome at night. And this is something which I always like to show, because it shows that a lot of people are still queuing up to get up there, and that's something which I as an engineer, I'm very proud of, that what we do is not just something which is a challenge for us. It is something which people accept, which people want to visit, and that's always good to queue. Not good to queue up, but it's good to see that a lot of people go there still. Another project, which was one of the earlier ones where I was involved as a project manager, is the dome, the roof for the Sony headquarters in Berlin. It's a combination of a steel structure with cables, with glass, and with fabric. It's Murphy, Yarn, and Arabs. What seems to be quite simple, it's you have a rotational axis, you have a hyperbole, you rotate it around at every 5 degrees, you take the shape with cables. Here you got two ridge cables, glass in between, a valley cable here, which would be quite an easy geometry, but what the architect then did, he rotated the central axis by 8 degrees and cut it off horizontally. What he then produced was something like an elliptical shape, which you can see here, which was the footprint of the atrium. And this is approximately 100 meters, this is 80 meters, so it's quite a size. The valley cables, all of them come together to a tension ring, which is not linked to any of the other elements, and the fabric itself is a structural element which avoids the whole roof to go up during uplift. And the king post in the middle is 45 meters long, and at the bottom point it's suspended back with the cables to the ring beam. The whole system sits on top of 5 different buildings in a height of 40 meters above ground level. One of these 7 supports is fixed. All of them are fixed vertically, of course. One of them is fixed horizontally as well, in both directions, another one horizontal in one direction, and all the others are sliding. So basically what it means, the buildings can move independent from each other, and it doesn't affect the ring beam. But internally, the roof itself is a highly sophisticated system with a lot of internal pre-stress. when you imagine one thing I briefly mentioned when I said we had to pre-camber the ramp of the Reichstag. When you look at this project, and when you imagine that this is something like an egg shape and you apply a lot of forces to it, you would immediately realize that this will move, it will squeeze, it will deflect. And actually the deflection in this direction where they squeezed together was more than 10 centimeters. To produce such a pre-stressed structure means to have the right length and the right geometry of all of the elements. To arrive at the right geometry for the ring beam means that I have to build a different geometry. So we had to calculate the geometry of the ring beam much wider and also with vertical bendings into it. So finally, once the loads are applied, the geometry we want to achieve is realized. What this also means is if this ring beam is wider and if you position all the elements in the right configuration, it is impossible to put in the first cable because the first cable would have to be stretched 10 centimeters more than it can be stretched. This was something we were really challenged with, and this is an aspect I want to add to this lecture here. We know what we want to achieve, we know what finally should happen, but sometimes it's extremely important to find a way to get there, and that's a good example for it. So what we decided to do after some long considerations is we said, what is the magnitude I have to shorten this kink post in the middle to allow all of the elements to be installed? And what we did is we lowered this top ring 50 centimeters so that we could install the first cables without overstressing them. We lowered the bottom point by 20 centimeters, which enabled us to put these cables in, which means that the whole system was 70 centimeters shorter. And once we had installed all the structural elements, we put a hydraulic jack at the bottom and we just opened it up like an umbrella. And with this system, we could pre-stress all the elements in one run. And I believe it was the only way really to achieve and to realize the building. Because one thing is quite clear, if you pull on one of these cables, it influences the other cables. So if you pull the wrong one, you might end up with something where you can work there for years and you don't achieve the final stress distribution. The whole ring beam had a weight of more than 500 tons. We've broken it down into 11 pieces with approximately 50 tons, a little bit less. And because of the size of 6 meters width and 6 meters height, we couldn't pre-assemble it in the workshop. We had to bring it to site and we created a pre-assembly area there to put it together at ground level and lift it up with cranes. When you look at the geometry, you can see here it's a tubular structure. You need brackets for the cables to link in, and as you can see here, it's quite a complex issue in itself. When you take down the cord, you can see from the marks of the stiffeners and the sequence of how the various diagonals are fitted in that it gets even more complex. This is a fabrication drawing for the brackets. That's how they looked like. This is what we did for the tubes. The end cutting of the various tubes was complex and of course different. We developed computer programs starting from the structural information where we created the elements and where we automatically generated the data for the cutting process and for the pre-assembly later on. Here you see how the elements arrived on site, because I said previously we couldn't do too much in the workshop. We had to bring everything to site. This is a good example. We marked the top point of the tubes so that we did know, once we know which tube it is, which end, which is the top point of it, to enable us to orientate it during the pre-assembly. And here you see the pre-assembly process. We had a template laid out. We laid out the 3 cords at the ground level. We fitted them together. We finally welded them. We lifted up the cords and then we fit the diagonals in. And as you can see here on these pictures, this is how it went up with using a huge mobile crane from the inside of the atrium. And here you see the almost complete structure. That's the last element which went in. What you also can see here is that we had to build up a temporary structure to build the kink post. We decided to build it in a vertical position right from the bottom level on. This is the principle I described before when I said we shortened the kink post. The way we did it, we had a solid bar in the middle with a length of 70 centimeters plus the extension into this block, and we shortened it during the installation, and then we extended it with the hydraulic jack with 1,500 tons capacity to fill in this green piece to finalize the pre-stress. That's the bottom part, which you just have seen in relation to people. When persons who have been, if you have been there, it looks up much nicer when you look up and in 20 meters height than it was in the workshop. But I think we needed these massive structures to cope with the loads. This is the top of the kink post, the top ring, where you see all the holes for the cables to go in. This is the bottom piece with the solid bar where we fed in this connection element. And what you can see here is once we had installed the kink post, we lifted it up vertically, we guided it within the temporary structure, and then we inclined it to 8 degrees and we only suspended it back by some cables. And then we discussed what's the best to install the rest of the structure. And it was, one of the ideas would have been to position a lot of tower cranes around the surroundings, because there was no chance in between the ring beam and the kink post to go through with a mobile crane, because we needed this space for our structure. And finally we decided to put the tower crane on top of the kink post, which was a really challenging issue. And there were not many people who believed that we really would do it. But as you can see from the pictures, it was done. We put the temporary structure in here, and we just got the crane up there with a chip length of 51 meters. And the capacity of the crane at the end of the chip was 3 tons, so it wasn't the smallest crane. With this crane, we pre-assembled the fabric areas. Of course, the fabric was cut short, as it has to be with the compensation, once it's pre-stressed to get the final shape. We pre-assembled it at ground level. We put all the bracketry onto it. We also integrated the ridge cable, and then we lifted it with this beam, and people were at both sides of the structure to link the cables into the system. We really tried to avoid to build up a huge scaffolding. It costs a lot of money, and it would have blocked all the other works ongoing on the site. So we had no scaffolding. And what you can see here is an upsailer going down and linking these fabric panels to the valley cable. This is a picture where you see these wrinkles, where you can see that it's not fully pre-stressed. It's the situation which we had after we had put all the elements together, still with the short kink post. Here you can also see the tension ring where all the valley cables come together. That's a pre-assembled picture from the outside, still with the crane on. And this is the hydraulic jack we had created ourselves, and this is how we pulled it apart. And here you can see the 70 centimeters already being free, and then we added the plates in there. This graph should show you how precise it was possible to calculate this operation. One thing, during the pre-stressing, the distribution of the loads within the cables changed. And before we started the pre-stressing process, we monitored the stress in all of the cables, and we adjusted it slightly to get to the pattern we needed to have to start this pre-stressing process. And what you can see here with these squares was the theoretical calculation which we did, and what you can see with the line is what the reality was. What you see here is the extension of the 700 millimeters finally, and this is the pressure in the hydraulic jack, which was then 15,000 kilonewton, which is 1,500 tons. And I was quite proud that it was possible to calculate it that accurately. What you can see here is a special phenomena. It's the wrinkling of the membrane. We had to wait at certain positions for 1 or 2 days to get the membrane to adjust, and if the yarns line up, we lose some of the pre-stress, which means that we did fall down a little bit, but then the tangent was the same as calculated, and I think the theoretical calculation and the reality were very close together. What we also did during the pre-stressing, we picked up the cable with the highest load and we constantly monitored it to be sure that we don't create any further forces into the system which we haven't calculated because you couldn't see it. And that's the final look down. That's the very tiny node, 20 meters up in the air, and that's the whole roof from the outside. The other project I wanted to touch, which is very close to here, which was our first project in the UK, and a really challenging one as well. It's the roof of the British Museum, Great Court, which is a triangular structure with triangular glass panes, and all of the panes have got different shape as well. We got 4,878 members with different end connections, with different geometry, and 1,700 nodes. That's a computer model. It's a Foster project, and Bureau Heppel as the engineers. One of the key things which you wouldn't pick up when you look at the roof at the museum was that we were not allowed to put any horizontal forces alongside the perimeter. The reading room couldn't be loaded because it's a very fragile structure. So what had to be done was to introduce 20 columns here which take the load at the center, and to have a perimeter beam here which only is vertically supported towards the buildings. So what you normally would expect, that this is something like an arch or a shell structure, is quite limited because with the restriction that no horizontal loads should be put in, it acts more in bending, and it's a complex structure. Here you can see what I just have described, the extra columns and the horizontal movement here. In order to understand the structure, we did run some analysis as well, and what you can see here is the deflection due to live load, and what you can see here, that it pushes out, means that there is no horizontal support along these edges. What you also can see, what's quite clear, is the areas where we have a double curvature, which was described earlier, are very stiff areas. Areas which are quite flat in one direction, they are quite weak areas, they deflect more. And of course, in such an area, the first buckling takes place as well. And it was very important to achieve the geometry quite precisely, because the buckling factor went down significantly. If we would have been 20 centimeters lower, it already went down to almost 1, which is unacceptable. Here you can see the detail of the roof at the perimeter with the sliding bearing. One thing which we did, of course, in order to achieve a straight line once we released the structure, when we built it, this perimeter beam wasn't built as a straight beam, it was built as a curved beam to the inside to compensate for the deflection which will come once the dead load is activated, which means that we have pushed the sliding bearing to the inside, which also gave us some comments from the clients and from the site team what we are doing. They want to have a straight beam, and I said, oh, well, we need to do this in order to achieve the straight beam at the end. This shows you the magnitude of deflection we were expecting due to dead load, and you can see that it goes up to 150 millimeters in that area, and this deflection was pre-cambered. So when we established the geometry which we needed to build the roof, we had to determine a different geometry to the end geometry, which is higher, which is amended to compensate for these predetermined deflections. The glass sits directly on top of the steel with some gasket system, with a stepped edge, with a flush outer surface, which means that the steel has to be very precise because the glass was produced at the same time and had to fit onto the steel here. See the glass shape. The biggest question at the beginning of this job was, what is the best, or how can we deal with the node? Because one thing I didn't mention, and I'll go back to the slide once again, the orientation of the beam is in equilibrium with the two angles. So this angle here and this angle here has to be the same one, otherwise the glass fixation and support detail wouldn't work. When you consider that further, and when you project a normal vector alongside each of these glass panes, you will immediately understand that these 6 members which come into the node, they come with a slightly different orientation. And to cope with that was the big question at the beginning. And here you see some of the node proposals which were rejected by the architect, and I think you understand why. But it was just to play and with the geometry to understand what is the implication of the geometry and how can we deal with it. Here, these steps are there not because of fabrication tolerances, they are just there in order to compensate for the twist, but of course unacceptable as well. And then we end up with the final geometry. What we said, we want to put the complexity and the costs in manufacturing this into one of the elements. So we decided to make a fairly easy node, which is cut from a plate perpendicular to the surface, and then we treat all the end connections of these members differently so that they fit into this gap created by the node and can be welded to it. That's the detail. To be sure that things which we develop on the computer works, we decided to make a very early model, which is this one, and it confirmed that we're on the right way. This is the testing, the structural testing to see whether the ductility is good enough to cover the bending moments, and it was successful. That's the next idea is how do we install it? How do we fabricate it? How do we install it? The museum is in the middle of the city. There's no way for any pre-assembly area here to build the roof up at the on-site at the roof level would have taken at least another half year or even more than that. So we said we start off with a triangle, which is the easiest and can be handled easily as an element. And then out of triangles we built ladders, which are prefabricated. The size of the ladders was determined in order to allow transport to site. And afterwards we have finished off these loose members on site. Here you see the principle of the triangle. There is a line which is the basic symmetry line, which is not in the middle of the profile. It is on top of it. But you also can see that a lot of the members are tapered because we got different heights of the nodes on the three sides. And from this baseline on, we developed a computer program where we have, using the structural information of plate thicknesses, sizes, we have developed a 3D model, which was then the basis for the workshop machines to cut the ends. And nothing was done manually, everything was programmed. That's the ladder. Here you see how we distributed the nodes on the sheets to be cut. What you can see also is we marked the center point, we marked the number of the node on one leg, which was a specific leg, because otherwise once you got it in your hands and you turn it around, you wouldn't find the right orientation anymore. The members were pre-assembled with overlength, then automatically welded with submerged arc welding. Then we laid them out, marked the center line, both ends, and the number, and we broke it down into different delivery parts so that we get the right elements to site on the right time. And then, with the information which was created from the computer, we got directly into the workshop. We amended a welding robot to a cutting robot. We got a turntable here. We cut one end, and then we turned around, we cut the other end. And the man at the machine, the only thing he had to do, he had to look at the number on the beam, and he had to find the same number on the screen, and then press the button, and the element was cut. There's still, and this was what this previous speaker said, there's still an element of logistics left, so you shouldn't believe that then the costs are the same as it would be a repetitive process and all of the elements are the same, because the logistics step in. But it's a step forward in order to minimize the extra costs and to make these kind of structures affordable. This is how we put the triangles together. It's quite simple. At the end of the day, it has to be simple, but it has to develop in great detail, because if it fails, it's fundamental. And then you can see how the triangles were put onto other jigs to get the ladders complete. And that's the ladder, how it came to site on the working platform. Here you see the ladders being installed and the loose members being fit in. Here you see finally painted structures, and the next step was to glaze the structure before it was depropped even. For the loose members, we had some tools to adjust them as perfect as they can be, because they also had to be in the right height, otherwise the glass wouldn't fit onto it. Here you see the beams with the temporary struts, and here you see how we have glazed the system. What you can see there is once we broke a glass pane, it took some weeks to get another one back because we couldn't put them on stock. All of them were different, but we haven't broken too many. The final challenge was to release the structure. You remember we said 150 millimeters in certain areas, and we had more than 600 props to just lower one after the other one wouldn't have been the right process for such a delicate structure. So we said we'll go in circles. We do 25% of the predicted depropping first, and we define 12 phases, and we deal with all of the props in the phase at the same time. We printed out data, how much each prop has to be released. We put it onto the props, and then we got people there to move it down in the right way. And so we lowered it down and finally got where we are now. What you can see here, that's a computer model from Foster's at the early days. That's what the reality was, and I think you can see that the reality comes really close to the computer model, and that's how it should be. It's a day-night. The glass itself is a body-tinted glass to reduce the light transmission. At night it looks much more transparent from the outside than during the day. I want to show you quickly another job which we're just working on, which is, you could say it follows the same principles as the British Museum, but it's another level of complexity. It's a job in Warsaw, and it's a 10,000 square meter roof over a shopping mall, and it's a project from Germany together with Epstein and Arup Sade engineers, and it's 7 spheres with connections in between. The architect said he put the handkerchief onto the spheres to get the shape, and it's supported with some trees from the inside. What I got here is also a small animation, if I can just go over to it. Where is it? Oh, that's the wrong one, sorry. No, that's the one which I wanted to show you later, probably. Go back. No, that's also the wrong one. I'm sorry. That's the gate set. It's an animation which was done by Epstein to show how the job will look like. Overrunning. I'm sorry. You just stopped me. I got some. Yeah, we'll see. I think it will be a fantastic structure. It's just we are to start on site within the next days, and we've already gone through half of the prefabrication, and we are ready to put the structure on top of this magnificent building. It's more than 10,000 square meters, so it's a approximately twice the size of the envelope from the British Museum. So it's a huge structure. That's a model. I said it was an extra level of complexity. When you look at the sphere, which is represented here, then everything is easy. The orientation of the elements towards each other lines up perfectly. The node is not the problem. The number one here is a saddle situation, and on a saddle situation, things get quite nasty, which I'll show you now. That's the detail, how the glasses fit on top of the, we are using RHS sections with some gaskets and the glass gets on top of it. Here you see the maximum angles. On the British Museum we had the center line running here. When we did this, the joints didn't line up anymore with this complex geometry, with the twist, which was much worse than on the British Museum, so we had to define these points as our basic symmetry points, which are on the underside of the glass pane, where we're working from, and the steel comes where it goes. Here you see these lines coming up, and everything underneath was projected from these lines. When you look at the node at the top, the center lines come almost together. The difference comes just from the distance of the gasket, because the perfect line is on top of the gasket and not on top of the steel. When you look at the bottom, you see what it means. This one goes into this direction, this one goes into that direction. It's almost impossible to put them together. And when we tried to use our British Museum node, we failed because it didn't look nice. Here you see another image how the bottom side works. That's the perfect node, which is at the spherical position, where you see that everything comes together nicely, no problem at all, top and bottom. And what we finally did, and this was a long development, we developed a twisted node, where the legs of the node are rotated towards each other, which is another level of complexity for the fabrication of the nodes. But what it achieves, and you will see that on the next one, I'll go a little bit faster, that's how they were twisted when you look at it from the top. And here you see the actual model on the top view, everything comes together. And on the bottom view, here you see it without the center lines. And when you look at it first, I think it looks quite logical. When you look at the lines, you see that with this node, we have just compensated the unregularity of the incoming members. Before I go to that, I want to show you now another animation which should explain how we're working. We, of course, have programmed it. It's twice the size of the British Museum, so we needed even more help from the computers in order to realize it in a quick and efficient time. Here you can see that we are selecting a part of the grid. This was produced by one of my engineers who has written the program. And the first thing he does is he puts in the elements just with overlength, and then he is selecting certain steps, certain modules, and then he is cutting. Here you see the come together offset. And the different orientations are put in, and here you see that the elements are cut, and this irregular node is created automatically with all the data being necessary for the machine in the workshop to be produced. What we also can do, what you can see here, we can define a gap between the node and the element, because if we produce everything with the right length, you got some tolerances in it, which means that the structure is growing. What we did is we did some tests and we calculated what is the gap we need to have to stay within the tolerances. And this was one of the measures we had in the computer program optimized so that we got the flexibility we needed. And I think now you will see how he pulls off one of these elements. Yeah. And how the members have to be cut to fit to the node. All of them different once again. I think I'll stop it. That's the top side where everything comes together perfect. So. I'll try to be fast. I got 2 more projects, but I'll go through it quickly. That's another project from Foster's at Gateshead, which is an interesting shape. It's a torus shape. It's from Foster's and from Heppold as engineers. And here you see that it's more than 10,000 square meters of panels as a rain screen. There is a membrane underneath. The water goes through the system into the rain screen and into the membrane, and it's taken away underneath the surface. Having a torus shape gives us one advantage, that we can work with rectangular panels, because on a torus we can fit 4 corners into a shape. Here you see the longitudinal and the transverse section. This is how the details work. All of the elements are different once again. That's the detail where the panel comes down and the glass continues on in the north, and this is the gutter which is hidden behind the panels, which collects all the water. That's a test piece we did. Flexible joints at the side wall, and this is how the panels are installed. Run through it quickly. And by now it is finished. I have got another animation here which shows you how the computer program works. I couldn't fit them into the presentation. The presentation crashed this morning. It was too many megabytes. That's the final product here. This is the grid where everything starts off with. It's quite a lightweight structure when you look at it at the end. And this is how a computer puts the profiles in and then cuts the profile, creates the lugs, the end plates, the stiffeners, everything. And all this information, which is automatically generated, is put into workshop drawings then, and is the basis for the fabrication and installation information. You see that the tertiary members coming in. Once the geometry is defined, once the data are defined, it's easy. Here you see the end plate, the holes for the bolts, the stiffeners. Everything has to be defined in general so that no manual interference is necessary. The principles have to be agreed, and then these things can be programmed to deal with the geometry in an economic manner. And here you see how we, at the same time, during building this up, we are producing the information for the workshop and for the fabrication and installation. And from the same computer model later on, you will see that the panels are integrated into it as well, and the information how to produce the panels is also optimized. That's the upstands for the panels. This is the substructure for the panels. Here you see the plates once again being created. And here you see the panels coming in. that? I think I've lost my other presentation, which is not good. That's what happened this morning as well. I thought I have overcome it. I think now. The last project I want to show is a project from Austria. In Austria there are not so many exciting projects happening, so we need to look at other countries to get the right level of challenge. But there's one exceptional project in Austria which was done. The client was the owner and inventor of Red Bull, which is an energy drink I'm sure you know as well. And he is the richest person in Austria. So what you can learn from that is you need to do the right things to earn enough money. And probably engineering and construction isn't the right approach. But I'm happy to be where I am, I have to say. But he has earned a lot of money. He owns a lot of old aircraft, and he is spending the money now. And the starting of the project was to create a hangar for the aircraft, where the aircraft can be maintained. And then from the beginning on, he was looking at the special shape. He wasn't happy with a normal hangar. As you know, they are like boxes. So what the architect produced there was an elliptical shape in both directions, an ellipsoid with a radial structure, which was rotated. The reason for that was, and I'll show you on the next, here you can see it, the rotation. The reason was that there was a building line which they couldn't exceed because the hangar is right next to the airport, sorry. Then we got two cylinders here on this side, which are sticking out as well. They are cut off along the same line, and they are integrated into the structure. Here you see the radial structure. I think you will understand that this is not very efficient to have such a bend, but this was what we have been asked for. And then we got two radial lines which didn't find the support. We were allowed to move these two cylinders around a little bit so we could find supports for the other ones. And the other issue we had problems with was we haven't got too much curvature here, so it was quite flat, and we had problems with buckling. So we said we need some sort of structure underneath to support it, and the architect gave us 50 centimeters, which is nothing for a span of 80 meters. We said we need 1.5 meters, and he said no for quite a while, and then he came back and said, yeah, you can have 3 meters. Because he got another idea, which I will show you. This part is now a bar. So he has created a sky bar in the center and another ramp to get up there. And now we got more than we wanted as a structural height, which sometimes it happens. Here you see the various sections. Here it's curving back. That's the longitudinal one, which is quite flat. And this is the short side, which is quite steep. I'll go a little bit faster. That's some technical details, how the wells come together, how the tubes, you can imagine that it's quite complex. We tried once again to put as big pieces as possible together in the workshop to have minimal work on site. The glass itself is flush, countersunk, laminated glass with a secondary structure which is of flats. Here you see the real picture. And this is how we built up the model once again. And we had to put all these brackets onto this curvature in the right position in order to get the glass and the secondary structure in. The red points you can see, but they should be in the next one as well, are the positions of the holographic targets. We built a model which we gave the surveyor and where he could monitor the various elements so they are positioned in the right order and the right place. The cutoffs are, it's not very visible, but the cutoffs are quite strange as well. We had to bend tubes, with non-constant radius to follow the ellipse. We marked up the line to get the position for the right elements. That's the central part, which I was talking about. Curved elements with N shapes. That's how we got the brackets in. Yeah, and finally I'll come to my ramps once again. There is one going up here, which is this one. There's a platform running at the same level to the front. And this was the ramp we got on later on to follow up to this sky bar, which is in the center here. Here you see the section of the ramp. It was quite interesting. The architect decided to make it a triangular section. So when you look at it, it looks like a flat piece of paper. You don't see the height here. The fixation of the glass balustrades is integrated, so there's no upstand here. So it really seems to be a flash element. What you can see here is, which sometimes makes life complicated as well, when you imagine that this is a private sky bar for the richest person in Austria, he wants to have each level of comfort he can have up there. So you've got lines for electricity, lines for water, for air conditioning and everything. And here you can see that these cables were put in the workshop before we put the deck plate in. And then it was protected and put in. That's the end beam, which is in between the hanger and the cylinder. And that's the product. And one more film, and then I'm gone. Which shows you how we have developed the ramp. Just need to find it. This is the sky bar up there, the ramp going up there, the cylinders. That's a public restaurant. And this is the basic line, as I have described it on the Reichstags project already. That's the basic system line where the ramp comes up. We once again have put the sections in a certain distance. Then we have combined the bottom and all the other lines. We got the twisted plates. Here you can see how the various plates are put into the system. And then we take the plates, each individual plate out of the computer. We unfold it to get it flat. We take the marks of the adjacent panes with us, and then we cut it. And then we put it into this template, and we fold them back so that we get, at the end of the day, the geometry which is necessary. Here you see how the various plates are created. And that's once the principles are agreed, that's once again something which can be automized, which can be programmed, and where all the data can be generated automatically. That's the deck plate. The other one. That's the tube, which runs on both sides. Second tube. Here you see the spotlights. That's the model which is the end product of this automatic process. And then we pull out the various plates to allow them to be cut. That's the workshop drawing which then is produced automatically, which doesn't look like a standard workshop drawing. And here you see once again the templates. They are adjustable because the inclination wasn't perfect. That's the other ramp, the lower one, which is hung from the main structure, which goes from the ground level to level 1. I think there are just 3 or 4 more images of how it looks like as a final product. Here you see the ramps, the sky bar. This was, oh, I should have put that earlier, I'm sorry. This is the first piece we have delivered to site, which went onto the central scaffolding, and then we put all the beams in. We supported them temporarily. That's the final bar. And here you see his aircrafts being parked in there. It got more than that. The biggest one here is a DC-6, which I'm not so familiar with aircraft, but I think it was the biggest propeller aircraft which was available. And there were two aircrafts still existing. One was from Tito, from the Yugoslavian dictator, which was sold to Africa and which was flying around there with tourists on tours, and the other one was from President Ford from the United States, and I think he inspected both of them, and he decided that the one from Tito is the best one to repair and to refurbish, and he has brought it in pieces to Austria, and now it's put together, and it will fit into the hangar. But it won't be a passenger aircraft anymore. I think inside it will be the most luxury aircraft you can imagine. So I'm at the end. I'm sorry for my overrun. Thank you.
Well, it was a detailed and thorough insight into the difficulties in the achievement of manufacturing some of the ideas we've been talking about, and I think that's a very important element to add. Now, it's been a long day. I think it's been a stimulating day too, and I think it'd be worth having some conversation. Obviously, this is the point where you as the audience can make points or put questions to the speakers, but could I ask the speakers to come up and assemble around the table? And I wonder, is it possible to raise the screen, or shall we move the table? Oh, I understand there's coffee and tea. What I would suggest in that case, if it's all right, is to get coffee and tea and bring it in here. Can we do that? And reassemble fairly quickly?